Welcome to part 3 on the module providing an overview of pattern relationships. In the first part of this module, we motivated the need for pattern collections to be extended, to go above and beyond what's there today. We also outlined some of the common types of pattern relationships that we'll be covering in this module. Part 2 provided a motivating example from the domain of avionics control systems in order to describe some of the key patterns associated with concurrent and network software for distributed real-time and embedded systems. This section starts to delve deeper into some of the pattern relationships. We'll be focusing on pattern complements and pattern compounds. We'll also summarize some additional patterns that you'll find in the Gang of Four and POSA books. The first topic we're going to discuss are pattern complements. There's a couple variations of this concept. In one variation, a pattern provides a missing ingredient needed by another pattern to make the resulting design more complete and balanced. For example, the Gang of Four book talks about the factory method. And the factory method is used to provide an interface for creating families of related objects without having to specify their concrete classes. And this is great. You can use the factory method to make objects that can be used in ways that don't require the users to know the details of how they're actually implemented. For some reason, the Gang of Four book doesn't talk about how to get rid of these created objects from the factory method. So some later work talks about something called disposal method. And if you take a look at the POSA 4 book, you'll find a description of the disposal method pattern. It encapsulates the concrete details of object disposal by providing an explicit method that cleans up whatever a factory method has produced, releases the resources, deletes memory, and so on. As an example of this pattern, or these pair of patterns, these pattern complements, in the context of our avionics computing example we were looking at before, Corba provides something called a portable object adapter, which is basically a manager for object life cycles. It creates the objects and destroys them. And it's also a demultiplexer that maps incoming client requests to the appropriate object implementations. And if you look carefully at the portable object adapter, or POA, interface, you'll see it has a factory method called createPOA that makes a POA, and a disposal method called destroy that cleans it up. Another example of pattern compounds is one where a pattern completes another or competes with another by providing an alternative solution to a related problem. For example, batch method competes with iterator by accessing elements of aggregates in bulk, thereby reducing communication costs. So here's the iterator pattern, which allows you to access elements of an aggregate or container without exposing the representation of the aggregate or container. And one of the characteristics you typically find with iterator is that it assumes there's very low overhead to get the next element, which makes sense if you're in a single-threaded standalone application. When you start running in a multi-threaded or distributed application environment, or more generally, any environment where there's latency sensitivity between the part that's iterating and the part that's providing the data to be iterated, the iterator can be very inefficient because you spend way too much time going back and forth across a round-trip boundary. A more effective pattern in that case, therefore, may be something called batch method, which groups multiple collection accesses together to reduce cost of multiple individual accesses in a latency-sensitive context. So what you would do there is you would make a call to a container or an aggregate and get back a group of elements which you could then iterate through locally without having to pay that round-trip expense and the latency that's associated with it. The next topic is pattern compounds. A pattern compound captures recurring subcommunities of patterns that are common and identifiable enough to warrant treating them as a single decision in response to a recurring design. For example, if you think back to the batch method pattern complement we just talked about, one way to represent this is as a pattern compound that combines the composite pattern from the Gang of Four book with the command pattern from the Gang of Four book. So a composite command encapsulates requests for an object, essentially hiding or shielding the users from differences between a single request and multiple requests behind a common interface. So for example, you could have a component interface or an aggregate or container that has a composite command, and you could send a set of requests or get back a set of results from that composite command. Once again, in the context of our Corba broker example, Corba defines an operation called send multiple requests one way that allows a client to initiate a variable number of requests, which could be one or could be many, in parallel, and it doesn't wait for the request to finish processing before returning control back to the caller. So that's an example of a composite command. Another example of a composite command would continue to riff on what we talked about earlier with batch method and iterator. It turns out that there's another pattern compound called a batch iterator that combines two competing pattern complements, iterator and batch method, to remotely access elements of aggregates which contain a large number of elements. Here's a diagram illustrating how batch iterator works. What happens is you go to the aggregate or the container and you get back a batch iterator which comes back with a chunk of elements to iterate through locally. And then when you are done iterating through that chunk, it goes back automatically and brings over the next chunk from the aggregate. This gets used in lots of different places. Corba has something called a naming service, which provides a batch iterator called the binding iterator that allows you to optimize bulk access to many, but not all, elements in a naming context. You can also take a look at the standard C library's buffered I/O operations like fgets and so on, which are also essentially batch iterators. And what they do is they grab a chunk of data, a buffer of data from an underlying file, and then they iterate through those locally, one at a time, efficiently, and only when the buffer is depleted do they go back and do the longer latency operation to get the next chunk from the file. So to summarize this section, pattern complements and pattern compounds are the initial steps towards moving away from patterns as isolated islands to more parts of an integrated whole that are woven together. And we've seen how pattern complements complete designs of other patterns. So disposal method completes factory method, for example. We've also seen how a pattern compound names a commonly recurring cohesive combination of other patterns as our batch iterator combined iterator with batch method to make it more efficient to access data without incurring the overhead of high latency. You can learn a lot more about pattern complements and pattern compounds by taking a look at the POSA 5 book, which has chapters on each of these topics with many, many other examples and goes into great detail exploring the different elements of these relationships and ways you can apply them to your program most effectively.